Orv, what happened to you?
Oh, the wind turned this umbrella inside out on me this morning, so I thought I'd bring it in here in the shop and maybe I can fix some of these ribs that got bent up. You know, trying to drag this thing through that wind almost made me late for the trolley.
Yeah, I'll bet dragging is the key word here as well. Something with this much area and that shape, you probably had to really pull to overcome the drag of that.
Sure did. The same is true for anything that tries to move through a fluid such as air. Drag is the resistance provided by the air towards something, anything, that tries to move through it. It's what you might call aerodynamic friction. It always works against you.
You know, as bicycle makers and bicycle riders, we're very acquainted with drag. If you want to go fast on a bike, you have to sort of lean over, or else the wind is going to push you back and slow you down. When I first got interested in aeronautics, I wrote to the Smithsonian, which was the NASA of our day, and I asked them for the latest information they had about flying. Well, they sent us 4 pamphlets, one of which contained information about what was known at the time about drag.
The information included this equation, which shows that the drag, D, is equal to a pressure factor, K, times the velocity, V, that's squared, times A, the area, times a factor, CD, called the drag coefficient.
You know, Orv, I think maybe it would be useful to students if we discussed each one of those terms in the equation in a little more detail. The first factor in the equation, K, is called the Smeaton's coefficient. It's a factor that was developed in the late 1700s as a reference pressure value, and it's equal to the drag on a 1 square foot plate pulled through the air at 1 mile per hour. V is the velocity. It's a special velocity called the relative velocity. So that's the difference between the air going over the wing or the wing going through the air. Those are sort of the same thing. A is the area. Now there's 2 areas that we can think of. One would be the frontal area. We talk about riding a bicycle, you try to decrease frontal area. The other area, as shown here in this equation, is the projected area. That's the area that you would see looking down on the wing. This is the area that's used in the definition of the lift equation, so it allows us to compare the equations on the same basis. The last factor, CD, is the drag coefficient. Well, this is kind of a complex factor that includes a number of variables, such as the shape and angle of the wings, the surface condition of the airplane, how rough or smooth it is, the stickiness of the air. This factor is usually determined experimentally.
You know, drag is really hard to measure in the air. Lift is certainly much easier because it counters the weight, and you know the weight of your aircraft so you can determine the lift. From our bicycle days, my brother said we leaned over. We decided to lay down on the wing to reduce that frontal area and reduce the drag. We were aware of that drag, but we weren't so aware of the drag that was produced by our wing shape. And that was such a factor when we made our 1901 aircraft. You can see here that when we made larger wings to gain lift, unfortunately we made them to be wider rectangles. The craft didn't perform well. In fact, it only provided about 1/3 the additional lift. So in the winter, we built a wind tunnel.
Yeah, you can see the wind tunnel over your shoulder. In the wind tunnel, we placed small models of the wings. We built these models out of tin here in the shop. And we would mount the models on what was called a balance. Now here's a picture of our balance. It's made out of bicycle spokes and tin, and under controlled condition, we would blow air across the model and measure the drag. We discovered that the drag for long, thin wings, as shown in this picture, produced less drag than short, fat wings, as we had on our 1901 aircraft. So in 1902, we used the information from the wind tunnel to build a new aircraft that had long, thin wings, had the same area as 1901, but the wings were very different shape.
And the performance really changed.
Oh, yeah, we set all the records in 1902 for gliders.
The wings of modern airplanes are all long and thin. They produce much more lift than they do drag. Engineers measure the amount of lift compared to the amount of drag to find out a lift over drag ratio, or L over D. The larger that number, the more efficient the wing.
You know, wings also have another source of drag called induced drag. The low pressure on the top of the wing and the high pressure below the wing cause the air to try to turn the tip. And in the turning of the tip, there's an additional drag factor. Long, thin wings have, in essence, a smaller proportional wing tip to the area of the entire wing, so long, thin wings have less drag.
A real recent innovation in aircraft is to bend the very tip of the wing up to reduce the tip-induced drag. This effectively sheds that wingtip vortex.
Maybe we ought to test that in the tunnel. What do you think? If I took a model and bent the tip up and put her, what do you think?
I don't know, it's going to add some more weight.
Yeah, you know, aeronautical engineers are always playing kind of a design game between lift and drag. To carry more weight, you need more to lift. And the things that you do to increase lift, like increasing wing area or going faster, also increase drag. So, particularly velocity, since lift and drag goes the square of the velocity. The faster you go, the more lift you get, but the more drag you get as well. Always a balance of factors in designing an aircraft. You have to find the design that maximizes the positive factors and minimizes the negative factors.
That's right. One final thing that we ought to make clear is that the motors on an aircraft are there only to overcome the drag, to move the plane forward. They're not there to provide lift. That's what the wings do. We could illustrate this with our 1903 aircraft. It weighed 750 pounds with a pilot, and it flew with an engine that produced only 130 pounds of thrust. That's because the motor didn't have to lift the plane, just overcome the drag.
Say, Orv, with all this talk of drag, I got an idea.
If you say drag something in the house, I'm going to have a conniption.
Well, all right, I won't say it. But let's go check and see what Charlie's up to.
Well, he ought to be done with that project by now, don't you think?
He's been working on this for a while, but I think it's going to work out all right.
Okay.